Welcome to the second part of our lesson on root finding. Today, we are expanding our toolkit to include solvers based on initial guesses and techniques for solving systems of nonlinear equations. By the end of this session, you will be able to distinguish between brackets and initial guesses, use SciPy's frosolve function effectively, and interpret your numerical results within a physical context. Remember that a root is simply a value where a function equals 0. In the previous lesson, we used robust methods like bisection and BrentQ, which require a bracket. Now, we will start by setting up our standard environment using NumPy, Matplotlib, and the Optimize module from SciPy. It is important to understand the difference between a bracket, which is an interval where the root is trapped, and an initial guess, which is just a single starting point. While guess-based solvers are powerful and flexible, the specific root they find can depend heavily on that initial starting value you provide. Let us start with a classic example. Solving cosine of x minus x equals 0. This transcendental equation has no simple algebraic solution, so we define the function in Python and create a range of values to plot so we can see where the crossing occurs. We finish the plot setup by adding labels and a dashed horizontal line at 0 to represent the x-axis. Plotting is a crucial first step in any root-finding problem because it helps us choose a sensible starting point for our numerical solver. Looking at the generated graph, we can see the curve crosses the x-axis somewhere between 0 and 1. This visual confirmation tells us that an initial guess like 0.5 is a very reasonable place to start our search. Now we call flysolve, passing in our function and the initial guess. Note that we extract the first element of the result because flysolve returns an array to accommodate systems of equations, even when we are only solving for a single variable. The output shows that starting from 0.5, the solver converged to approximately 0.739. The residual, which is the value of the function evaluated at this calculated root, is extremely close to 0, which gives us high confidence in the result. As we move forward, remember that FOLV is designed to be versatile. However, you must always check that the residual is near 0 to ensure the solver did not get stuck or fail to converge. Many nonlinear equations have more than one root. Consider the cubic function x cubed minus x. We know analytically that this function has 3 roots located at -1, 0, and +1. We will plot this cubic function between -1.6 and +1.6. By overlaying the known roots as individual points, we can clearly see how the function behaves and where it crosses the 0 line. The plot reveals 3 distinct crossing points. This highlights a key limitation of numerical solvers. They will usually only find one root at a time, so we need a strategy if we want to locate all of them. Here, we iterate through a list of different initial guesses to see where the solver leads us. For each guess, we run flysolve and print both the resulting root and the corresponding residual to check the accuracy. Notice how the result changes based on where we start. Guesses near -1.5 lead to the root at -1, while guesses near 0 converge to 0. This clearly demonstrates why your choice of initial guess is so critical. The lesson here is that a solver is not a magic tool that finds every root automatically. You should always use a plot to identify different regions of interest, and then apply appropriate guesses or brackets for each specific root you are looking for. So, which solver should you choose? If you have a clear interval where the function changes sign, BrentQ is typically the most reliable choice. However, solve is necessary when you move beyond a single variable to a system of equations. In this specific test, both methods yield the exact same root at +1. It is often good practice to compare different methods to ensure the stability of your numerical solution. Now we will tackle a system of 2 nonlinear equations representing a unit circle and a line. To solve this using fonsolve, we must first rearrange both equations into a residual form, where they are set equal to 0. We define a single function that takes a vector of variables and returns a list containing the residuals for both equations. After providing an initial guess for both x and y, PhiSolve iterates until it finds values that satisfy both equations simultaneously. The solver identifies the solution at roughly x equals 0.89 and y equals 0.45. By printing the residuals, we can confirm that both equations in the system have been satisfied to a very high degree of precision. Visualizing the system helps confirm our numerical work. We will plot the unit circle using trigonometric functions and the line y equals x over 2 to see where they actually intersect in the coordinate plane. Finally, we add the solution point we just found onto the plot as a scatter point. This visual check is essential for making sure we have found a physically meaningful intersection rather than a mathematical artifact. The plot confirms our calculation perfectly. The orange line passes through the blue circle exactly at our solution point, showing that our two-equation system was solved correctly by the guess-based solver. Let us apply this to a real physics problem. Calculating the terminal velocity of an object with quadratic drag. At terminal velocity, the gravitational force mg is perfectly balanced by the drag force c times versus squared, resulting in a net force of 0. We define our net force function using specific values for mass, gravity, and the drag constant. We will generate a plot of net force versus speed to visualize how the force changes as the object accelerates. The curve starts at the object's weight when speed is 0 and decreases as speed increases. The point where this curve crosses the dashed 0 line represents the terminal velocity we are trying to find. Since we have a clear sign change, we use Brent Q to find the velocity that makes the net force 0. We can also verify this numerically by comparing it to the analytical solution, which is the square root of mg divided by the drag constant c. The results match perfectly at about 7.49 meters per second. The net force at this speed is on the order of 10 to the negative 13, which is essentially 0 given our computational precision. Beyond just getting a number, you need to perform diagnostics. We can write a simple helper function to automate residual checking, ensuring that the function value at the root is within a strict tolerance, such as 10 to the negative 8. We apply this check to both our earlier trigonometric example and our terminal velocity calculation. Developing the habit of verifying your residuals will save you from trusting incorrect data in more complex simulations. As shown in the output, both solutions passed the residual check. This confirms that the solvers converged correctly to points that truly satisfy the original equations we defined. Avoid common pitfalls like treating solvers as a black box or ignoring the physical meaning of the units. A good root-finding workflow always includes defining the equation clearly, inspecting the function visually, and verifying the final residual. Now it is your turn for some guided practice. Try defining a new system representing a circle with a radius of 2 and a horizontal line at y equals 1. Use PhiSolve with an initial guess to find the intersection and then verify your results. For this practice problem, you should find a solution where x is approximately 1.73. This exercise reinforces the process of packing multiple equations into a single function for the solver to process. To wrap up, root finding is a fundamental skill for solving physics equations that cannot be handled algebraically. Whether you use brackets or initial guesses, always remember that numerical reasoning requires a combination of graphs, solvers, and careful residual checking.